This particular video, we are going to discuss about pause frames. Now, what is this pause frame? Let us try to understand. So, let us consider two devices. One is sender and another is receiver. Now, let's say if sender is sending some data and receiver is receiving that particular data using this eternal frame. Suppose, let's say device A is transmitting basically at the speed 1 Gbps, and device B can be able to process the data or receive the data at 500 Mbps only, because it might be due to some reasons like CPU may be busy or DMA is slow or internal buffers are almost full. In that particular cases, it might receive the data at slower speeds. Let's say here the incoming rate is 1 Gbps, but the processing speed is 500 Mbps. Then there will be almost the lost of our packets which was sent by our sender. Now, in this particular case, what is that we are going to have? Let's say if our receiver buffer is almost full, then definitely there will be a loss of the packets. Now, this leads to retransmission or throughput reduction or network congestion or performance degradation. This and all is going to happen. Now, in this particular case, due to this particular reason, we are going to use something known as pause frame, which is introduced in IEEE 802.3x, which is nothing but it is a special Ethernet frame sent by the receiver to the sender. Okay, so the receiver, it is going to tell the sender that to stop or pause the transmission using this particular pause frame. Now, what is this pause frame going to have? A pause frame is basically a special Ethernet MAC control frame, and it is going to have IP information, TCP, UDP, ARP, ICMP informations. And pause frame is not going to have all these particular things. Normal Ethernet frame is going to have this information, whereas pause frame is only going to have flow control information. Now, exactly what is pause frame is going to contain is it is going to contain header information, MAC control information, and CRC. Whereas your normal frame is going to contain the actual payload data like header, actual payload data, and CRC. Right now, where is this particular pause frame is going to operate? Is it is going to operate in the data link layer. So that's the reason it is not going to involve any software protocols, or we are not going to have any TCP IP involvement. The Internet MAC is going to control this particular pause frame. Now, what exactly this pause frame is going to have? The pause frame is going to have destination MAC address, source MAC address, type, opcode, and pause time over here. So, how much time it should stop? It is going to be referred over here in the case of my pause time, and FCS. That is nothing but my frame check sequence. Now, so about this destination MAC address, source MAC address, Ethernet type, opcode, we already know. Now, coming to this particular pause time. So this field tells the sender how long to stop the transmission. So whether it should be nanosecond, or it should be millisecond, or it should be microsecond. No, we are not going to describe this pause time in terms of nanosecond, microsecond, millisecond. We are going to mention this in a unit which is known as pause quanta. Now, what do I mean by this pause quanta? So basically, pause quanta is nothing but it is a standard which is framed by IEEE 802.3 specification, and basically it defines the interframe gap as 96 into bit times. So pause quanta is nothing but 96 into bit time. What do you mean by bit time? Bit time is nothing but the time you are allocating for transmitting a particular bit is nothing but my bit time. Okay. So for one cycle, in terms of, if I want to talk in terms of hardware, for one cycle, how for one cycle, uh, if you're going to send one bit of data, then what is the time of that particular cycle? Okay, that is nothing but my bit time, the time you are going to allocate for sending a particular uh, for sending a particular bit is nothing but my bit time, or the time period of one cycle is nothing but your bit time. Okay, now, so this means that after transmitting one frame, a station must wait for this particular time required to transmit 96 bits before starting the next frame. For example, let's say if our network speed is 1 Gbps, and one bit time is nothing but 1 second divided by this number of bits, which is nothing but 1 into 10 power minus 9 seconds, 1 nanosecond. So for transmitting one bit of data, you're going to allocate 1 nanosecond. Then for 512 bit times, you're going to take 512 into 1 nanosecond. Or in this IEEE 802 point standard, you're going to take 96 into 1 bit time, which is nothing but 96 nanoseconds. So this is nothing but my interframe gap which the transmitter should allocate. So it is going to pause the transmission for 96 nanoseconds. This is what we are going to do. But here, what is going to happen if we observe over here? Let's say the time required to transmit one bit is nothing but time taken is 1 divided by 100 into 10 power 6, which is nothing but 10 nanoseconds. That means you are going to allocate for one bit, you are going to allocate 10 nanoseconds. Okay. And 96 into 10 nanoseconds is nothing but 960 nanoseconds, which means IFG is basically 960 nanoseconds over here. But over here, if we carefully observe, for at 10 Mbps, we are going to allocate time required is 100 nanoseconds, and 96 into 100 is nothing but 9.6 microsecond. In this 10 megabits per second, the IFG is basically 9.6 microsecond. Now, here, let's say the interframe gap requirement is basically 96 bits. Okay, 96 into bit time, right? That means 96 into the time required for transmitting a single bit. Okay, so this is nothing but time for one bit, right? But if you have carefully observed, in the case of my MIA transfer, we have already discussed that for one cycle, we are going to send 4 bits of data, right? So that is the reason the time required for sending 4 bits of data over here, if we carefully observe over here, but over here, in the case of my MIA, I'm not going to send 1 bit per cycle. I'm going to send 4 bits per cycle. That is nothing but 96 into bit time will be nothing but 24 into nibble time. So that means 24 into nibble time. So you are going to take 24 into nibble time. IFG will be now 24 into nibble time. That means for one cycle, I'm going to take, basically, I'm going to send one nibble, right? So that's the reason IFG is nothing but 24 into nibble time. And internally, I'm going to process 1 byte of data. So my TX is going to process the data for one cycle. It is going to process 1 byte of data. In the previous modules also we have seen. So that means IFG will be now, if you again divide 24, um, if you are going to divide, you are going to get 12. So which is nothing but 12 into byte time, because for one cycle you are going to send 1 byte of data. That means if you further divide it 24, you are going to get 24 divided by 4, you are going to get 12. Okay, so this is what you're going to, sorry, I mean 24 divided by 2, you're going to get 12 into byte time. Okay, so this is nothing but my IFG. So 12 into the time required for sending a byte, which is nothing but my interframe gap. So if I can develop a counter which is counting the number of cycles, basically a counter is going to count this number of cycles, right? So if the counter is counting 12 number of cycles, then I can indirectly achieve this IFG, which is nothing but 12 into byte time. So if a counter can count 12 number of cycles, it is basically achieving this particular IFG. And what we are going to do in our, since we are developing transmitter side now, so transmitter side, a counter will be counting 12 number of cycles. That means it will be basically waiting for completion of this IFG. After completion of this IFG, we are going to restart, or else we are going to pause for that much time period. So this is how we are going to do the coding. Now let's see what is that we are going to have. So let's say if I'm going to have this module, which is transmitter underscore IFG, where it is going to have clock and active low reset, and speed underscore select, which is also optional, and IFG underscore start. Okay. And this IFG underscore start is basically going to indicate to start of an interframe gap. Okay. And it's also an input. And IFG underscore active to indicate the receiver that interframe gap is active. And IFG underscore done is to indicate that interframe gap has been completed. Now I'm going to take a counter which is basically going to have the initial value is 11. Okay, IFG underscore count is equal to 11. Why? Just now we have discussed it. Now I'm going to have a counter which is going to count for that number of cycles. Now if I'm going to apply active low reset, my count will be equal to 0. IFG active is 0 and IFG done is equal to 0. Else, I'm going to basically wait for this IFG underscore start and IFG underscore active is equal to 0. If these two conditions are met, then my count value will be equal to 11 and IFG active will be equal to 1. Now, if IFG active is equal to 1 and count is equal to 1, then I'm resetting all the values or else count will be decrementing. See, so count will be decrementing and IFG active will be 1 itself. So after reaching 12 into byte cycles, then only I'm going to make this count is equal to 1. If count has been made to 1, then count will be equal to 0 and IFG active will be equal to 0. That means interframe gap has been completed and IFG done is equal to 1. So this is how we are trying to include the interframe gap in the packet, and this is how we are going to basically receiver is trying to send the pause frame and transmitter is basically pausing the frame using this interframe gap concept. Yes, so that's about this particular video. If you like this video, please like, share and subscribe to my YouTube channel all about VLSI. Thank you for watching this video.